Hello, welcome again to the second lecture of digital signal processing. In first lecture, we have brief introduction to what is digital signal processing, why we use digital, why we use frequency, and then we had a basic understanding of how DFT is derived from various other Fourier analysis methods. So today we'll go ahead and we'll see how actually DFT is derived from DTFT. So in first slide, I will explain the drawback of DTFT. As we all know, the DTFT is used for discrete time and aperiodic sequence, and its corresponding spectrum is continuous as well as periodic in nature. So it will be very lengthy, and a digital computer cannot process that frequency domain data as it is continuous in domain. So we have to discretize it so as to make our computer enabled to process that data. And when we discretize that data, we realize that the periodic data discretized will result in very large amount of samples. What we are interested in is only one period out of that. So the discretized spectrum with only one period, that will give us a pair called as a DFT, where we have both time domain and frequency domain data discrete, as well as both have only one period. The discrete Fourier transform has been developed to convert that continuous function of omega to discrete function of omega, that is frequency. Here very important to note that only time is discrete in DTFT and not frequency, but in DFT both time and frequency are discrete in nature. This is a slide which I have used from the previous lecture. Those who have not seen this can visit my previous lecture. The link is in description down. And what we discussed there is this is a periodic signal, its corresponding DTFT. If it is sampled, I get this, and one period from this sampled version makes my DFT. And this is periodically repeated, and this is sampled. This becomes actually a DTFS pair. But very important to note that DFT and DTFS is not same. As I said in a previous lecture, this is just a nature of how our graph or spectrum looks like. It's not actual amplitude. We have not talked about actual amplitudes. This is just a nature, periodicity or continuous discrete. So actual nature of DTFS and DFT will be different, and that can be learned by having a look at this slide. Though we have not learned DFT yet, the equation of DFT, but still it has been used here to compare it with DTFS. What DFT is? DFT is x of n into e raised to minus j 2 pi by n into nk. And if you compare that with DTFS equation, which is actually similar to the CTFS formula that we have already learned, then by comparing we see that DFT coefficient x of k is equal to capital N times of DTFS coefficient Ck. Okay, so relationship between DFT and DTFS has been established here. X of k is equal to n times of Ck. So more precisely we can have this representation. We have a n length aperiodic sequence whose DTFT is continuous frequency spectrum. If it's sampled and if this is periodically repeated, then the relationship between this and this is this thing is n times of DTFS of this. Okay, we understood how we get a nature. If this is periodically repeated, this will corresponding frequency will get sampled. This we have understood. So actually this is n times DTFS of this, and relation between this and this is DFT. To compute a DFT of sequence x of n, we have to sample its DTFT, capital X of e raised to j omega, over a finite number of frequency points, and that is mathematically expressed as x of k, that is DFT, is equal to x of e raised to j omega sampled at omega is equal to 2 pi by n into k, where k varies from 0 to n minus 1. What is this thing and this thing? If you remember, I said digital spectrum or that DTFT spectrum is periodic with period equal to 2 pi duration. If we have to sample that 2 pi duration into capital N equidistant points, then the spacing between two samples will be 2 pi divided by capital N. Okay, and that each location will be identified by using index k equal to 0, that is 2 pi by n times of 0, 2 pi by n times of 1, 2 pi by n times of 2, 2 pi by n times of 3, and so on. So we have omega k is equal to 2 pi by n times of k, where k varies from 0 to n minus 1. So those sample locations actually look like this when capital N is equal to 4. If this idea is not clear, let's have a look at this sampling of one period of DTFT to obtain DFT. We have not discussed about amplitudes yet. We are just discussing frequency axis and time axis. So for example, if we have n is equal to 4, we have to sample omega in 4 equidistant points between 0 to 2 pi. So what will be those locations? Locations will be omega k is equal to 2 pi by n into k in general. So n is 4, so 2 pi by 4 into k, where k varies from 0 to 3. After k is equal to 3, what will happen? After k equal to 3, k will be equal to 4, where the values of omega will start repeating. As you can see here, this is a location 2 pi by 4 into 0. This is a location with k equal to 1. Values of k are represented here, and values of omega k are represented here. So for k equal to 2, 2 pi by 4 into 2, k equal to 3, 2 pi by 4 into 3, k equal to 4, 2 pi by 4 into 4, which is nothing but 2 pi, which is same as 0, one complete revolution. So this sample is same as this sample, if you have understood now. So k has unique values from k equal to 0 to k equal to 3. After k equal to 3, the same samples will get repeated. These samples are repeated. So we can conclude that in general for n point DFT, we sample DTFT over values of k equal to 0 to k equal to n minus 1, which will give us a unique set of samples over one period. Here we have DFT and IDFT formula, which is derived from DTFT and IDTFT formula. If you notice, there is only two differences between DFT and DTFT formula. The first difference is, as sequence is aperiodic and has limited number of samples, this range, which was minus infinity to plus infinity in DTFT formula, now it becomes 0 to n minus 1 in DFT formula. This is first difference. And second difference is, here we had e raised to minus j omega n. Now instead of omega, we have 2 pi by n into k, that is 2 pi k by n. This is second difference. These two same differences are reflected here in a IDFT formula. In IDFT formula, you can see that this is 0 to n minus 1, this is e raised to plus j, instead of omega I have 2 pi by n k into n, and instead of 1 upon 2 pi, now we have 1 upon capital N, because period we are considering capital N number of samples. After n number of samples, it repeats itself. So where k is a frequency index, n is a time index, these both run from 0 to n minus 1, and capital N is a period. The alternative simple formulation is, instead of writing e raised to minus j 2 pi by n into nk, we can replace e raised to minus j to 2 pi by n by w, and we can rewrite these both formula like this. where this W itself has a negative power inside it. That's why DFT formula will have positive Kn and IDFT formula will have negative Kn as a power. And this W is called as a twiddle factor. We'll see in more detail how that simplifies our calculations. Now if you look at this signal X of n, it has 5 samples and its corresponding DTFT is computed over a range minus infinity to plus infinity, and we get this blue waveform. The DTFT is this blue waveform. And if I compute DFT by using this only 5 samples, because the rest of the samples are 0, so if I compute DFT by using these 5 samples, I will get the red samples as shown here, which are actually the sampled version of DTFT. This red are the sampled version of blue waveform. So this is DTFT and these red samples form a DFT. You can see that for DTFT period is 0 to 2 pi, after that it repeats, and for DFT period is capital N equal to 5 samples. After 5 samples it repeats itself. So the n-point DFT is computed from a sequence X of n with length L in such a way that capital N should be greater than or equal to L. What I mean to say is the larger point DFT can be computed for a smaller length sequence, but reverse is not true. Why? Because if we compute capital N point DFT where n is less than L, then the IDFT may not result in the similar sequence back again. Just switch to the next slide. If n is greater than equal to L, then there is no aliasing, means X of n, its n point DFT is X of k, its n point IDFT is again X of n. Why? Because we have used capital N greater than equal to L. Now if we don't do that, if we use n less than L, then aliasing occurs, and because of which the n point DFT, which is X of k, cannot result in n point IDFT, which is same as X of n. So the frequency spectrum of DFT, as we have seen all other spectrums, can be described in two different parts. First is a magnitude spectrum or magnitude function, which is mod X of k, which is defined like this, mod X of k square, it's generally plotted, and the phase spectrum, which is tan inverse of imaginary part upon a real part or argument of X of k. Both magnitude spectrum and phase spectrum can be a discrete spectrum plotted with respect to values of k equal to 0 to n minus 1. Now we will discuss some important properties of DFT. First property is linearity. If we have DFT of sequence x1k as a capital X1k and DFT of another sequence small x2k as capital X2k, then the linear weighted combination of these two sequences will result in a DFT that is nothing but the linear weighted combination of two individual DFTs. As you can see, DFT of x1k and DFT of x2k are linearly weighted. That forms a DFT of this whole sequence. Second property is periodicity property. If we say that time domain sequence is periodically repeated, if it is periodic, then the corresponding frequency domain spectrum also will be periodic with same number of samples as that of a time domain sequence. Before we move to the third property, that is circular convolution property, we'll see a circular shift, what is called as a circular shift. If in a non-periodic sequence, the shift that is observed, the conventional shift that is observed, that looks like this. For example, suppose this is a sequence which is to be shifted towards left by 2 samples, then it will look like this, the lower one, this. And if that sequence is periodic, then the shift will not be same as this. It will be different. And to see how it will look like, I will first periodically repeat that sequence and I will produce this graph after periodic repetition. After periodically repeating, now I will introduce a shift of 2 units towards left. So what happens? This 5 will come out, this 4 will come out, and at the same time this 5 will come in, this 4 will come in. So if we observe only one period in between these two vertical dotted lines, it looks like initially we have 5 4 3 2 1, and after 2 times circular shift, that is shift in a periodic sequence, we have 3 2 1 5 4. Why do we call it as a circular shift? Because this 5 appears to be moving out and getting inserted from this side, from right side. Next time this 4 comes out and gets inserted from this side, and we have this new sequence. So it looks like as if the sequence is connected from back to back as a ring, and when we shift this out, that same sample comes in from other side. That's why we call it as a circular shift, and it is observed in a periodic sequences. So the circular shift by m unit towards left in a periodic sequence x of n with period capital N is represented as x of n plus m. If it is towards right, then we have x of n minus m, and it always has capital N at the bottom to represent it is a circular shift in a periodic sequence with period capital N. Now we'll see circular time shift property. If we time shift circularly by m units, then the corresponding DFT will get multiplied by, if we time shift by m units, the DFT will get multiplied by e raised to minus j 2 pi k by n into m. This is same as an operator e raised to minus j 2 pi by n into nk, where n time variable is replaced by m. If you remember previous video lecture, in that we have discussed, here as it is a frequency domain data, nowhere we can have index n, time index n. So instead of n, we have the fixed time shift value, that is small m. If we perform time reversal, then equivalent time reversal will be observed in a DFT data. The conjugation property says that if x of n is conjugated, then its corresponding frequency domain data, the DFT, will be x conjugate of n minus k. Means it is conjugated and time reversed. Circular frequency shift says that if we introduce circular shift in a frequency domain, that means this. If we introduce circular shift in a frequency domain, remember the definition of circular shift, connected back to back. So if we introduce circular shift in a frequency domain, I will have multiplication with operator e raised to j 2 pi by n into mn in a time domain. Again, this is same as a previous one. The only difference is, as it is a time domain data, we cannot have variable k. Instead, we have shift amount m. Now, as we all know, we have learnt in a DTFT also, the time domain multiplication is equivalent to frequency domain convolution, and time domain convolution is equal to frequency domain multiplication. That same is true for DFT also. The time domain multiplication is equal to frequency domain convolution with a scaling factor of 1 by n. Convolution for periodic sequences is generally called as a circular convolution, because periodic sequences appear as if those are connected back to back in circular fashion. So if we have circular convolution, definition is like this: x1m into x2 of n minus m. By now you just start with this definition of circular convolution: x1 of m into x2 of n minus m. This is circular shift in a second sequence. The convolution property of DFT says that the DFT of circular convolution of two sequences is equal to product of individual DFTs of those two sequences. So it looks like this. It will be product of DFT of first sequence and DFT of second sequence. Next property is on circular correlation. Like how we have convolution, we also can have correlation, which is generally used to determine the degree of similarity between two different signals or two similar signals. Degree of matching can be found by using correlation. So correlation is defined something like this. This is somewhat similar to convolution. So in frequency domain, we have product of two DFTs. First DFT as it is and second DFT is conjugated. As in convolution, we have y of n minus m and correlation y star of n minus m. So that is obvious that here also you will have a star, that is conjugate. For more details, you can refer any documentation and you can see the derivation for convolution and correlation and how we can find properties for them. At the end, we'll see a Parseval's relation. As we have Parseval's relation in DTFT, that energy can be found by using frequency domain data also. Here also we can find energy by using frequency domain data. We can multiply x1k with x2 conjugate k. We can sum all such products and scale by 1 by n, we will get energy. Or we can find the product of these two signals, summed product of these two signals. Now we will move to the important concept called as a circular convolution. As I said, circular convolution is used in periodic sequences. To perform circular convolution of two sequences, it is necessary that both the periodic sequences should have equal period, that is capital N. It should not happen that one sequence is shorter, other sequence is longer. We cannot perform circular convolution. This is first important necessity. And the output produced by using that circular convolution will also have the equal length as that of the input sequences. This is the definition of circular convolution: x of m into y of n minus m summed over m equal to 0 to n minus 1. So the second sequence, as you see here, is a time reversed and shifted sequence. Why time reversed? Because we are having a dummy variables m and minus m, that as it is a minus m, it is time reversed, and we are shifting by n amount every time we want to find new output sample. So this can be also represented in some other form where y of m is a fixed sequence and x of n minus m is a time reversed and shifted sequence. These two forms are same for circular convolution. So if I expand first equation where x is fixed and y is a reverse and time shifted version, then I have output z of n is equal to, if I substitute values of m in these indices, x0 y of n minus 0, x1 y of n minus 1 and so on, x2 y of n minus 2 and so on, x of n minus 2 y of n minus n plus 2, obvious because m is to be substituted, then x of n minus 1 y of n minus n plus 1. So you can verify this. This is the expanded version of this summation sign. Now if I substitute n equal to 0 to calculate the first output sample of this circular convolution, then what will happen? I will substitute n equal to 0 here, I will get this. I will substitute n equal to 0 here, here, here and here, and that gives me this thing. So x of 0 y of 0 minus 0, x of 1 y of 0 minus 1. So I can rewrite this equation as this: x0 y0 plus x1 y of n minus 1 plus x2 y of n minus 2 plus dot 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 y2 xn minus 1 y1. Now this same previous equation is used for reference, and now I am substituting n equal to 1 for getting second output sample. So if I substitute n equal to 1 in this equation, here, 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 here and here, I will get this thing. You can verify. And now if I simplify this again, I will have this x0 y1 plus x1 y0 plus x2 yn minus 1 and so on. What happens here is, here I have y0 yn minus 1 yn minus 2, and here I have y1 y0 yn minus 1 and so on. Look at the x in x samples, x0 x1 x2 fixed, x0 x1 x2 fixed. So x is fixed, y is getting shifted. See, this y0 got shifted from this location to this location. Now it was multiplied with x0 earlier. When I calculate first sample, that y0 is now getting multiplied with x1, so it got shifted to right. See, this was yn minus 1 was multiplied with x1, and now it is multiplied with x2. So if I go ahead and keep on substituting for each new sample, if I substitute n equal to 2, I see that now y1 gets shifted to the right, y0 gets shifted to the right. So every time I do this, these y samples get shifted to the right. What actually happens is, the last sample y2 comes in and gets multiplied with first sample of x0. So it's like this. Okay, so it appears as if one sequence x of m is fixed and the other sequence is getting shifted circularly in a computation of each new output sample. So we can find circular convolution in three different ways. Before we understand how it is actually done, we'll see what are these three methods. First method is a matrix method. Second is a concentric circles method. These are both time domain methods. And the third method how we can do that is a DFT IDFT method, which is frequency domain method. So in the first method, what we do is we have matrix multiplication, where this x is a fixed and y is written here. You can see that this y is copied from the previous equation. So for z0, I want to multiply this row with this column. So actually x0 into y0, x1 into yn minus 1. Where have I obtained it from? If I go back and back, see here, z0 is x0 y0 x1. So these y values, yn minus 1 yn minus 2 and so on, these all y values are written as it is in that matrix at the first place here. Similarly, from equation z1, I have copied all values in the second row. From equation z2, I have copied all y values at third row and so on. If you observe, this first row itself is a time reversed version of original sequence y of n. What is time reversed sequence? The first sample remains as it is and rest of the samples get reversed. So y0 and remaining samples are from yn minus 1 to y1 reversed. And in all other rows, what I am doing is simply shifting this last sample to the first place and rest of the samples are towards right. Another commonly used symbol for circular convolution is like this. It represents what point circular convolution I am converting. N point, n equal to 4, n equal to 8, n equal to what is value of n, that is being written here, and a circle around it represents that this is a circular convolution of these two sequences. Let's see an example of circular convolution of these two sequences. Both have length equal to 4. So we want to perform circular convolution. So matrix multiplication, where a maximum matrix dimension can be 4 by 4. So I will have two matrices. First will be the reversed second sequence, second will be the fixed first sequence, and in third block we will have a convolution output. So this sequence 2031 is to be written here because it is a fixed sequence. We can use this as a fixed and this as a time reverse sequence, doesn't matter, but we at first place we have learned by using first equation, so I am explaining with reference to the first equation. So I am using this as a fixed sequence here and I will be using this as a second sequence. So time reversed will be 10, 40, 30 and 20. So I'll write it. I'll write by shifting last sample to the first place and shifting all other samples towards right. This is time shift, circular time shift, if you remember. Another circular time shift, 30 will come here and rest of the samples towards right. Another time shift. And in second matrix, a vector which is fixed input sequence 203 minus 1. Now if I multiply this, I will have output like this. Okay, and finally the output is a 90, 130, 50, 130. As I mentioned, if we perform circular convolution of two equal length sequences, the output will be also same as the input length sequences. So there is a 4-point input sequence and 4-point output sequence. Now the another way of doing this is a concentric circle form of circular convolution. At first it might feel little difficult, but it's easy to do. What we do here is, here we are considering n is equal to 4 again with the same input sequences. What I am doing is I am writing first signal as it is. Okay, signal 1 is x of n, signal 2 is h of n. I am writing first signal as it is. What is that? 203 minus 1. I am considering that this is a sample at origin, the first sample, 203 and minus 1. I have written it in a anti-clockwise direction. So first sequence is written in a anti-clockwise direction. As we want second sequence to be time reversed, we'll write that second sequence on similar circle but in clockwise direction instead of anti-clockwise. So what we'll have? We'll have second sequence written in a clockwise direction. What is that? 10, 20, 30, 40. So it is 10, 20, 30, 40. I have written second signal on a circle in a clockwise direction. Now what I will do? I will see individual locations and those concurrent samples I will multiply and I will find out this product. So I will multiply this 2 with 10, I will get product 20. Similarly 0 into 40 is 0 and remaining 2 samples also multiplied with to get this final product. If I add all such product values, I will get first output sample at n equal to 0. Why? Because I have simply written time reversed signal. I have not provided any shift. So it is for first output sample at n equal to 0. Now to introduce a time shift, circular time shift, I have to rotate this second time reversed signal in a anti-clockwise direction. This is very important. What I did, the fixed sequence in an anti-clockwise direction, second sequence in a clockwise direction, and then rotation in an anti-clockwise direction. So anti-clockwise, clockwise, and then anti-clockwise, anti-clockwise, all rotate. So rotation of this sequence in anti-clockwise direction will result in this. 10 will go here, 40 will come here, and so on. So 10, 20, 30, 40. Now what I will do? With this first fixed sequence, again I will multiply sample by sample to find a product. So 2 multiplied by 20 is a 40. Likewise, I will find all 3 products and finally I will add all of them to get a second output sample at n equal to 1. We repeat this for every new output sample till n reaches n minus 1. So this is n equal to 0, this is n equal to 1. We have to find for n equal to 2 and n equal to 3, because 3 is nothing but n minus 1. In this case n is equal to 4. So we'll do it and we finally get this. This is one again anti-clockwise rotation, this is one more anti-clockwise rotation, and these are products, and all products have to be summed to find output sample. Finally output is this, and we can verify that the answer found using matrix method and by using concentric circle method are same. Now there are efficient algorithms are available for computing DFTs and IDFTs of finite duration sequences. Therefore, it is computationally efficient to implement these convolutions by using frequency domain method, that is DFT IDFT method, the third method that we are going to discuss now. I hope you remember this, the property of a circular convolution of DFT. Circular convolution in time domain is equal to product in frequency domain. Let x1 and x2 are two different length sequences to be circularly convolved. Now this might be confusing because I said both the sequences should have same length. If those are different length, then we can do something that I am explaining now. So two different length sequences. First one, make length of both the sequences equal by padding extra zeros at the end of smaller length sequences, so that it becomes same length as that of the another sequence, the longer sequence. Then in second step, you compute n-point DFT of a first sequence and n-point DFT of a second sequence individually. Let's call them as a capital X1 of k and capital X2 of k. In third step, you find product of those two DFTs, capital X1k multiplied by capital X2k, call it as a Z of k by using a sample by sample multiplication. And at the end, you find IDFT of Z of k will be same as Z of n, which is circular convolution of two sequences x1n and x2n. So very simple method, find DFTs, multiply, find IDFT. We'll see in more detail how we can do circular convolution using DFT IDFT in next lecture.